Okay, so the next thing to do is that for any equation in rectangular coordinates, we can convert the equation into an equivalent one in polar coordinates, keeping in mind that sometimes when we get to the origin, the equation blows up for division by zero. But in most cases, we can for most points we can convert the equation from its rectangular form into its polar form. So just consider, for example, the equation y equals x squared for the standard parabola. Let me show you how to do that. Essentially, what you do is you use these conversions between x and y. We already saw before why x is y. The conversion between rectangular and polar is x equals r cosine theta and y equals r sine theta. So what I do is basically every place that I see an x, I replace it with r cosine theta, and every place that I see a y, I replace it with r sine theta. So the way that's going to work here is I'm going to take the y and replace it with r sine theta, and I'm going to take the x and replace it with r cosine theta. So I have y just goes to r equals sine theta, and the x squared becomes r cosine theta quantity squared. So what I'm going to do is just manipulate this algebraically a little bit. This gives me r sine theta equals r squared cosine squared theta. Since I'm going to want to solve for r in terms of theta in order to get a function, let me just divide through by r. So this is going to give me sine theta equals r cosine squared theta. Let's come up here. So this is going to give me r equals sine theta over cosine squared theta. Simplifying this a bit, I get sine theta over cosine theta times 1 over cosine theta. That gives me r equals tangent theta secant theta. So kind of surprisingly, this turns out to be the equation of a parabola in polar coordinates. It's kind of surprising because we have the very simple equation y equals x squared, but I can also write this equivalently as r equals tan theta secant theta. Just to give you some idea of what this means, what it means is that if I were to draw, let's say, a line of a radial line at 45 degrees, that's going to be pi over 4. If I ask the function to tell me how far along this radial line I should go, it's going to give me this point. And if I were to draw a different radial line at let's say 3 pi over 4, and I asked how far I should go, it's going to tell me the same number, but now of course we're going in the other direction. It's going to give me that point. And what if I asked it about the radial line pi over 2? Notice that there's nothing directly above this parabola. There are no points in that direction. I can go as high as I want. I'm not going to find any points on the parabola. No surprise, because tangent and secant are both undefined at pi over 2. They would give infinity. So there's an example of so here's an example of how to convert a fairly familiar rectangular form into its equivalent polar form. Okay, so let's consider another typical equation for which we know what the equation looks like in rectangular coordinates. Oops, it's not what I wanted to write. There we go, 2. So let's suppose we have y equals 3x plus 1. So not that anybody should need this drawn for them, but basically this is just going to be this line, right? So let's see, what does that look like in polar coordinates? So what we do is, once again, we replace y with r sine theta, and we replace x with r cosine theta. So this is going to be 3 r cosine theta, and then plus 1. So we have r sine theta equals 3r cosine theta plus 1. Since we're going to want to solve for r in terms of theta, we want to get all the r's on one side, so that's going to be r sine theta minus 3r cosine theta equals 1. We factor out the r, giving sine theta minus 3 cosine theta equals 1, and finally that gives us r equals 1 over sine theta minus 3 cosine theta. So Kind of strange. Y equals 3x plus 1 is about as simple as an equation gets. It's about as simple as a curve gets in rectangular coordinates. This, of course, looks like a very, very difficult function, and that's just kind of how things work in polar coordinates. Things that are kind of easy in rectangular end up being fairly complicated and obscure in polar coordinates, and vice versa. So let's do two equations that you know in rectangular coordinates that actually tend to be fairly important in polar coordinates. This is something that you're going to have to be able to do more or less automatically if you take Calc 3, so might as well learn it now. So x equals 5, which is of course just the vertical line passing through the point 5, 0. Let's see what that looks like in polar coordinates. Once again, we replace x with r cosine theta, and that is equal to 5. So constants, of course, just remain what they are, so we simply write r is equal to 5 over cosine theta, which usually simplifies as r equals 5 secant theta. So that's the equation of the line x equals 5. And for y equals negative 3, we're going to have, let's see, replace y with r sine theta. That equals negative 3. That gives us r equals negative 3 over sine theta, which of course is going to be r equals negative 3 cosecant theta. That's an equals sign. So there we go. Okay, so basically, one thing that you probably want to make a mental note of is that the equation y equals a becomes r equals a secant theta, or sorry, x equals a rather. So a vertical line is written this way. Line x equals a is r equals a secant theta, and the line y equals b, that becomes r equals b cosecant theta. That's how you write a horizontal line in polar coordinates. So that's something that's worth making a mental note of.